Sorry for the delay, everyone. I need to check and make sure that I have the volume turned off on this before I get underway. Oh, I did not have it turned off. Okay, welcome everyone. I hope you enjoy this brief lecture today. I wanted to talk to you a little bit about distance sensing, and I thought this would be interesting. Dr. Kelly talked about distance sensors today in the face-to-face class. He did a great job. It was pretty interesting. If we could have just had you there, we'd have been playing around with distance sensors together. But I thought it would be interesting to talk about some of the technological advances and the methods that are used in order to measure spatial characteristics, in particular distance. Usually when we think of spatial characteristics, we're thinking of, point A, point B, somewhere on the map. And in this case, we're going to be talking about spatial characteristics in terms of how far is, for instance, the top of a plant from the sensor, and that can be used to measure, for instance, the plant height. You know how tall or how high the sensor is, measure the distance from the sensor to the plant, and you know how tall the plant is by extension. These have a lot of different applications. There's a good chance that you have these on your cell phone. They're on vehicles, like, when you're backing up and your car starts to beep at you. That's using a distance sensor to measure the distance between your back bumper and whatever the signal's coming in contact with. There are a few different types of distance sensors, and I'm just going to run through a few of them today. I tended to pick them based on a combination of sensors that I've used, sensors that I'm familiar with, and a few different technologies that you might see out there. The very first one I would like to talk about is this one right here. It's an infrared proximity sensor, and this uses infrared radiation, and based on, it sends out an infrared signal, measures the signal coming back, and you're able to calculate distance based off of that. Now you might be thinking, how do we get a sensor that is so accurate in terms of time that it can measure the amount of time that light travels from the sensor to the object and back? And the reality is, with the infrared sensor, we don't. The infrared sensor is based on the idea that you send out infrared light, and based on the reflected light coming back, if the reflected light is stronger, it's an indication that, oh, hey, we're pretty close to the object. If the light is weaker, then we must be further away. Now, obviously, because of this, it's very sensitive if you have interference from another type of radiation source, such as sunlight. I'm not 100% certain what wavelength is used for these, but be aware that if your wavelength is too short, you're going to be affected by sunlight. And if it's too long, you're going to be affected by radiation from other objects, such as the Earth and, other things like that. And so there are some limitations with this sensor. Because of that, we often use a sonar or an ultrasonic sensor. The first one of these that I used looked exactly like this on the right here. And all it does is it works very much like the sonar does if you're on a submarine. Sends out a signal, it measures the amount of time that it takes for that signal to come back, and based on that, it's able to calculate distance. We calibrated and tested these sensors several times during the time we were working on a remote sensing project. They were always plenty accurate in terms of what we needed them to do. In fact, they were more accurate than our ability to make repeatable measurements, because if you mount these on a tractor or a sprayer, you're driving through the field, the whole contraption's bouncing up and down a little bit. It's moving left and right, so it's not even necessarily hitting the very tops of the plant. But we got nice repeatable measurements. We were able to publish a couple of papers. And interestingly enough, we talked a lot about remote sensing and how you can use, for instance, NDVI or another remote sensing index to measure plant growth. One of the interesting things we discovered was that if you only measure plant height, the R-squared value between plant height and total biomass is like 0.8 or 0.8 plus. And so with a very simple measurement system, we were able to get a pretty accurate estimate of the growth of the plants. Now, keep in mind, anything that allows a plant to grow taller but does not cause it to put on more leaves is going to mess a little bit with that equation. But as you can see, this is just a sensor right on a bare circuit board here. Because we were worried about our sensors getting wet, we actually moved to this weather resistant version. Same type of thing, but now it has both restricted field of view and it also protects the sensor. And this end here attaches very nicely to a screw-on 1-inch PVC pipe, if I recall correctly, or a 3/4 inch PVC pipe. And so it's easy to build something up that's weather resistant without having to put a whole lot of work into it. You do have to solder the connections, so it's not completely plug and play off the shelf, but it worked out really well for what we were doing. Now, another type of technology that you often see to measure distance is LiDAR. And all LiDAR is light detection and ranging. And so very similar to these other sensors, you use light to send out a signal, and based on the return of that signal, you can measure the distance of objects. And the cool thing about this is you can actually do it in 2 dimensions or 3 dimensions simultaneously. And so this picture here, you can see they've actually run multiple scans. And with these scans, not only do you see the proximity change as you're going deeper in, but you can see these individual ridges and other things that give you a 3-dimensional fill that might not be evident if you're using something like this, which is essentially just giving you one measurement at a time. And, something like the LiDAR can give you a bunch of measurements at a time. You see LiDAR a lot on aircraft. One of the big challenges of LiDAR is its expense. LiDAR tends to be very expensive. You can get an expensive LiDAR for, maybe several hundred or a few $1,000s, but, high quality, high resolution LiDAR has traditionally cost, anywhere between $50,000 and $250,000. And so, and you don't get any colorimetric information with it because it is just a signal propagation technique. It's not able to tell you what color things are. And so as you can see with this picture, they lit it up differently based on the distance from the camera, but it's not telling you strictly anything about, these look like trees, but are we certain that they're actually trees? Are they green? Are they yellow, etc.? So that's traditionally been one of the limitations on this end. Something that more recently has become really popular in some of your newer cell phones with the original Xbox was this sensor that is able to measure 3-dimensionally and can do it for a lot cheaper than you can with LiDAR. Plus, it also gives you an overlay of color on top of it. This type of sensor uses the concept of structured light. And I went ahead and just pulled this up because it gives a reasonable example of the concept of structured light, which is this. If you send out an infrared pattern of light, and the sensor knows what that pattern is supposed to look like, the size of it, the shape of it, etc. The distortion of that light is related to the distance of various features that are detected by the sensor. And so you have a reference image that says, okay, if we're aiming at a flat panel, this is what this pattern should look like. And then as soon as you add objects in there that are not flat, such as this person's hand right here, that changes the structure. And based on those distortions, you can get very accurate measurements of distance of that object from the sensor. So, to me, this is fascinating that just by measuring this distortion of light, you're able to get a three-dimensional image. This has become very popular. You see it in a lot of different applications today. Now, there are also other methods of measuring three-dimensionality. One that has been used for many, many years is stereo imaging. And there are a few different ways that you can even do stereo imaging. One way is by taking two cameras, having them a set distance apart, and each of them are shooting images simultaneously. And so if you close your left eye, or sorry, yeah, I'll pretend that this is my left eye. I'm mirrored on this camera, so I'm opening my left eye, but it looks like to you like I'm opening my right eye. I see the world in one way. If I switch eyes, you can see how everything kind of shifts over. Well, our eyes are actually doing stereo imaging based on the difference in what one eye sees and what the other eye sees. These cameras work in the same way. It turns out that you can measure the distance of objects from the sensors based on the difference in orientation of what the left one sees and what the right one sees. So one way to do it is, as I showed, to use two sensors simultaneously. Now, the military for probably 70 or 80 years or more has done this with single cameras. And the way that they do that is they fly at a set speed, and they're just taking pictures constantly, time over time. And so they're actually getting this, the stereoscopy through multiple images that can then be compared with the image in front and behind and used to create a three-dimensional image. And so you can very accurately and rapidly measure three-dimensionality using these types of methods. Here's an example of stereoscopic imagery. They're just talking about it in details here. But some of the areas that this is used currently, we're doing a three-dimensional phenotyping project where we're using 3D cameras to measure the plant structure of different cotton cultivars. I've seen three-dimensionality used for remote sensing using UAVs. In fact, thinking back to what we were just talking about. In fact, let me see if I can find a picture here. 3D UAV. Because your UAV is capturing a bunch of images simultaneous, or one after another, and it's keeping track of location with a GPS unit while it does it, you can get very nice three-dimensional structured images using your UAV. Now, you should be aware of this. This image here might actually be 100 or 1,000 or 10,000 individual images that are put together through the use of computer processing to create this three-dimensional image. And in my experience, this process is very taxing on the actual computer. So if you're going to try to do this, you better have a pretty robust computer or have a lot of time that computer can devote to this process. I hope you've enjoyed this lecture, and I will look forward to talking to you next week. As soon as I figure out how to end my presentation here. Have a great weekend, and I will look forward to talking to you soon.